All right, let's take a look at chapter 6-7. We're going to look at polygons in the coordinate plane. So we're going to take all of those properties about special quadrilaterals and triangles we've learned in the last couple chapters and put them into use when we're looking at a polygon that's in the coordinate plane. So we're looking at it on top of the xy axis. Each vertice has a point that it's associated with. We're going to talk about how we can identify these certain polygons. So to do that, we'll be using things like the distance formula, slope, and the midpoint formula. So they're all put here in the beginning as a nice little review for you. Keep these handy as you work throughout the practice problems and your homework problems. Just as a little review for those formulas that we talked about earlier this year, and I'm sure in classes before this class as well. So the first example we're going to look at here, we're given a triangle in the coordinate plane, triangle ABC, and we're asked to classify it as either scalene, isosceles, or equilateral. So before we can even start to approach this problem, we need to make sure that we know what each of those terms mean. What is a scalene triangle, what is isosceles, and what is equilateral? Again, review from semester 1, a scalene triangle is a triangle that has no congruent sides. An isosceles triangle is a triangle with 2 congruent sides, and an equilateral triangle is a triangle with all 3 congruent sides. So we need to figure out how many congruent sides we have in this triangle in order to classify it by one of those terms. Now, when we're looking at a polygon, any figure in the coordinate plane, and I want to know how many congruent sides there are, I need to know the length of those sides to determine if they're congruent. Do not do this by simply looking at my picture and saying, yeah, all 3 sides look like they're probably congruent, it's probably an equilateral triangle. That is not going to be a sufficient approach. We need to have the math to back it up. So, how do I determine the length of each side? Well, to use length, to find length, we're going to use the distance formula. So, if I can find the length of all 3 of these sides, I'll then be able to determine what type of triangle I have. So I'm going to start, I'm just going to jot down here the distance formula. It's up there in that chart as well, just as a little reminder, so as we're filling in our points, we know exactly where those values are coming from. And another thing I'm going to do before I go ahead and get started is I'm going to label what each point is, so I can just look at that instead of having to count each time. So my vertex A is at the point 0, 1. My vertex B is at the point 4, 4. And vertex C is at the point 7, 0. So now I've got my distance formula. I've got all 3 of my vertices listed as points. Let's go ahead and use that distance formula to find the length of each side. I'm going to start with AB. You can start wherever you want. And go ahead and plug in the x2 and x1 being the x coordinates of A and B, y2 and y1 being the y coordinates of A and B. You can do this in either order. It does not matter. Try and be consistent. So if your numbers are in a different order than mine, you'll notice you'll still get the same answer I do. So I've got 4 minus 0 squared and 4 minus 1 squared. I'm taking the square root of all of that. And simplify, 4 minus 0 is 4. 4 squared is 16, so that first set of parentheses turns into 16. 4 minus 1 is 3. 3 squared is 9. So now underneath my radical, it's the name of our square root, I've got square root of 16 plus 9. 16 plus 9 is 25. So I've got the square root of 25, and the square root of 25 is 5. So we've just found that AB has a length of 5. Let's continue. I'm going to go ahead and move on to BC. Again, you could do these in any order you wanted. And plugging in 4, 4, and 7, 0 as my coordinates. My x's are 4 and 7, so I've got 7 minus 4 squared, plus my y's are 4 and 0, so 0 minus 4 squared. Again, if you did it in a different order, that's okay. Square root of all of that and simplify. 7 minus 4 is 3. 3 squared is 9. 0 minus 4 is 4. 4 squared is 16. So underneath the radical, I've got 9 plus 16. Again, 9 plus 16 is 25, so I'm looking at the square root of 25. And the square root of 25 is 5. So BC also has a length of 5. So we can already, where we're at, rule out scalene triangle. We know that this is not a scalene triangle because a scalene triangle has no sides congruent, and this figure has at least 2 congruent sides. So now we need to determine whether it's isosceles or equilateral, and we're going to do that by finding the length of our last side, side AC. So A and C, I'm going to use 0 and 7 for my x's and 1 and 0 for my y's. So I've got 0 minus 7 squared plus 0 minus 1 squared. Oh, that should be 1 minus 0. It would work either way, but let's be consistent. So 1 minus 0 squared. And the square root of all of that. 0 minus 7 is negative 7, but negative 7 squared is a positive 49. Any number, a negative number times negative number is positive. So negative 7 times negative 7 is positive. 1 minus 0 is 1. 1 squared is 1. So underneath my radical, I've got the square root of 49 plus 1. 49 plus 1 is 50. Now, in your textbook, right before you hit section 6-7, is a review on how to simplify radicals. I'm going to assume that you've done this in Algebra 1. If you haven't, if you've never seen this before, let me know and I'll go over it with you some more, or visit that section in your book. Simplifying radicals means any time that there's a perfect square inside that radical, go ahead and pull that out. Meaning, I don't want to just throw the square root of 50 into my calculator and get a decimal, because then I have to round, and that's not exact. But I want to have the smallest exact number I can have. So I'm going to rewrite the square root of 50 as the square root of 25 times 2, all underneath that radical. Because 25 times 2 is 50, and 25 is a perfect square. Rules of radicals say I can separate that into the square root of 25 times the square root of 2. And we just said that 25 is a perfect square, meaning the square root of 25 is 5. So I can rewrite root 25 as 5, and then I'm still left with square root of 2. So that's kind of a minor section of what we're doing here, but a good review for you. If you've never seen it, go ahead and visit that. Now what do I have? I have AB is 5 units long, BC is 5 units long, AC is 5 times the square root of 2 units long. Well, 5 times the square root of 2 is not the same length as 5. It's going to be bigger. So in this case, AB is congruent to BC. I have 2 congruent sides, meaning I have an isosceles triangle. Okay. Our next problem, we're given a figure and we're told it's a parallelogram. It says is, and then we've got this little symbol. Remember from earlier in this chapter, if that symbol exists, that symbol means parallelogram. So we're told it's a parallelogram. We want to know if it's a rhombus. Is parallelogram ABCD a rhombus? And explain how we know. Now, we know a lot of things about rhombuses. So there are a lot of different approaches you could have here. We know that the sides have to all be the same length. So we could use a distance formula to find the sides. However, another thing we know is that in a rhombus, the diagonals have to be perpendicular. And we know the converse of that, saying if your diagonals are perpendicular, then it's a rhombus. So I'm going to use that property to determine if this is a rhombus. And the reason I'm doing that is because that's going to take less work than doing the distance formula 4 times. It's not right or wrong. It's just a little bit more efficient, a little bit faster. So you can approach these however you want, but in this case, I'm going to use the fact that the diagonals, if the diagonals are perpendicular, then it's a rhombus, because it's just going to save me some time in my calculations. So we need to know if the diagonals are perpendicular. Now, remember from semester 1, we talked about perpendicular lines and slope. And we said if the slope of 2 lines are opposite reciprocals, then the lines are perpendicular. So I'm going to need to find the slope of my diagonals. My diagonals are the ones in blue here, AC and BD, and decide if they're opposite reciprocals. And if they are, then I've got perpendicular diagonals. So I'm just going to go ahead and refresh with writing the slope formula here. Y2 minus Y1 over X2 minus X1. And they've already written in our points for us here, so we don't have to do that step. So I'm just going to go ahead and start by finding the slope of one of my diagonals. Let's do BD first. So the slope of BD, you can pick either point to be x1, y1, and the other point to be y2, x2, y2. I'm going to go ahead and call B to be x2, y2. So I'm going to take my y coordinates, 4 minus the y-coordinate of D, 1, divided by the x-coordinate of B, 0, minus the x-coordinate of D, 1. So 4 minus 1 over 0 minus, that should be a 2. I apologize. The x-coordinate of D is 2. I was looking at the wrong thing. So 4 minus 1 over 0 minus 2. Always simplify what's on top and what's on bottom separately, then do your division. 4 minus 1 is 3. 0 minus 2 is negative 2. Reduce if you can. In this case, that's all I can do. So I know the slope of BD is negative 3/2. So without even going forward yet, let's talk about what we would need to have in order to have perpendicular diagonals. Lines that are perpendicular have opposite reciprocal slopes. Opposite meaning change the sign, reciprocal meaning flip the fraction. So in order for this to be a rhombus, AC would have to have a slope that was the opposite of negative 3/2, so it'd be positive, and flip the fraction, 2/3. So if the slope of AC is positive 2/3, then I have a rhombus. Let's check. Slope of AC. Again, I'm going to pick, in this case, I'm going to pick C to be my x2, y2. So 5 minus 0. Oh, I did that. Yep, 5 minus 0. Over 4 minus negative, which is plus positive 2. 5 minus 0 is 5. 4 plus 2 is 6. Slope of AC is positive 5/6. 5/6 is not the reciprocal of 3/2. So since my diagonals are not opposite reciprocals, they are not perpendicular, and therefore this is not a rhombus. Again, you could have taken a different approach. You could have tried to find the lengths of all 4 sides. You would have noticed at some point that they're not all the same. But I tried to do one that was a little bit more efficient. You can choose how you do it. And our last one, a little bit more intensive. So again, we're going to be asked to classify a quadrilateral, but it tells us we have a kite at the right. So remember what we learned in section 6, a kite has exactly 2 pairs of consecutive congruent sides. And we want to know the most precise classification of the quadrilateral formed by connecting the midpoints of the sides of the kite. So there's a lot going on there. This is what we really need to know. We want to know the quadrilateral formed by connecting the midpoints of the sides of the kite. So we're going to make some quadrilateral inside that kite, and that's what we're going to end up classifying. So let's start by making that quadrilateral. We're going to make it by connecting the midpoints, so we need to find the midpoints to get started. And again, I'm just going to start by jotting down the midpoint formula. As a reminder, add the x's, divide by 2, that's your x-coordinate. Add your y's, divide by 2, that's your y-coordinate. So let's start. We're going to find, I'm going to call it point A, and A is going to be the midpoint of KI. Now again, I want to go ahead and label all of my points just over here on the side so that I don't have to look at them each time I have them written down. So K is the point -4, 0. I is the point 0, 4. T is the point 8, 0. And E is the point 0, -4. So I want to find A, and A is going to be the midpoint of KI. I'm going to use K and I for my x1, y1, x2, y2, plugging into my midpoint formula. So I get -4 plus 0 divided by 2, 0 plus 4 divided by 2. And that gives me -4 plus 0 is 0. Let me try that again, excuse me. -4 plus 0 is -4, divided by 2 is -2. 0 plus 4 is 4. 4 divided by 2 is 2. So A is the point -2, 2. I'm going to go ahead and plot that right here. There's A. Let's do B, and I'm going to call B the midpoint of IT. So I've got 0 plus 8 divided by 2, 4 plus 0 divided by 2. And simplify, 0 plus 8 is 8, 8 divided by 2 is 4, 4 plus 0 is 4, divided by 2 is 2. So the midpoint of IT, we're going to call that point B, is the point 4, 2, and I'm going to plot that. C, we're going to call the midpoint of TE, and I'm going to get 8 plus 0 divided by 2, and 0 minus 4 divided by 2, or plus negative, either way you want to look at it. Again, 8 plus 0 is 8 divided by 2 gives us 4. 0 plus negative 4 is negative 4 divided by 2 is negative 2. So the midpoint of ET, we're going to call that point C, is the point 4, negative 2, and plot that. And the last one we're going to call point D, and that's going to be the midpoint of KE, negative 4 plus 0 divided by 2, and 0 minus 4 divided by 2. Simplify, negative 4 plus 0 is negative 4 divided by 2 is negative 2. 0 minus 4 is negative 2 divided by 2 is negative 2. So my last midpoint is the point negative 2, and plot that. So now I've got my endpoints of my quadrilateral. I'm going to go ahead and draw in the segments connecting each of those endpoints so we can see what picture we're looking at. So here in green is the quadrilateral that is created by connecting the midpoints of each side of the kite. Now we're asked to classify that. So there are, again, multiple approaches to solving this, to identifying what type of quadrilateral that is, but I'm going to notice something right away. I'm going to notice AB and DC are both horizontal lines, and AD and BC are vertical segments. And we learned back when we talked about lines, parallel and perpendicular lines and their slopes, anytime you've got horizontal and vertical lines intersecting, they're going to be perpendicular. That was a theorem we had. So what does that tell me? That tells me each one of these angles is a 90-degree angle. Since I've got horizontal and vertical lines intersecting. Now I need to determine my side lengths in order to determine whether I've got a rectangle or a square. Again, I could use the distance formula, but I want to be as efficient as I can. Anytime we've got horizontal and vertical lines, we can find the length of each side by just counting. We don't actually have to use that distance formula. So I'm going to count. I'm going to start by finding the length of AB. I'm just going to count how many units it is from A to B. So 1, 2, 3, 4, 5, 6. AB has a length of 6. BC, again, I'm just going to count from B to C. 1, 2, 3, 4. DC, 1, 2, 3, 4, 5, 6. And AD, from A to D, 1, 2, 3, 4. So notice here, my horizontal sides have a length of 6, and my vertical sides have a length of 4, meaning opposite sides are congruent, and I've got right angles. Anytime I've got opposite sides congruent and all 4 right angles, I'm looking at a rectangle. ABCD is a rectangle. Not a square because my side lengths are not all the same, so we stop there with rectangle.